turns out that we almost never have just a naked proton. Protons are in chemical environments, right? They're around other atoms like carbon and oxygen and nitrogen and sulfur and all double bonds and triple bonds, and those are different environments. So since the nuclei are surrounded by a cloud of electrons, those electrons can block out some of the external magnetic field in a process that's important to understand called shielding. So you're literally being shielded from the external magnetic field. So let's look at this a little bit in detail down below. Let's see what this has to say if we look at this first kind of scenario. So here we have a naked proton, right? Just a single H atom. External magnetic field outside, B outside, 14,100 Gauss. Well, it's naked, and we saw before that at 14,100 Gauss inside that we process at 60 megahertz. We're 60 megahertz right here. So that comes in, and then here we have absorption occurring. So we see that we'll be NMR active in this situation. So there's resonance occurs. So this one looks good. Right now, in a magnetic field that now let's look at the next one. So what we're going to have on this next one is now this kind of nucleus around us, okay? And in that nucleus, let's imagine that we have, or surrounding the nucleus, let's imagine that we have electrons. So that's an electron cloud here. It doesn't matter how many there are. Electrons move, and when they move, they generate a magnetic field. And that magnetic field can either add to the external magnetic field or subtract away from it. So in this shielding case, what we're going to imagine is that you have an external magnetic field outside of 14,100 Gauss. And as that energy comes in and passes through that electron cloud, we subtract out 10 Gauss. That's just a number I'm picking out of a hat, basically, right? So 10 Gauss here. So that means that inside that nucleus, you actually only experience outside magnetic field of 14,090. In other words, it says B inside, but that's what you feel inside because you've subtracted off 10 Gauss here. So if you want that proton to process here, down here and flip up to a higher energy state, then you need to crank this thing up to compensate for the loss of 10 Gauss. So we're going to crank it up to 14,110. And that way, as that light comes through, that RF frequency comes through, we come down here and we lose 10 from this, but now we have 14,100, and at 14,100 we have resonance occurring. So we see a peak show up on our NMR spectrum. So this continuous wave view of NMR is something that you see occasionally. And when you do see it, you'll see references to the following terms on spectra. So one of the things that you'll see, of course, we've got shielded over here on the right-hand side and de-shielded over here on the left-hand side. These shielded protons are going to require a stronger magnetic field to resonate at a given frequency. That frequency will be constant, remember, in CW. It's the magnetic field that varies. And de-shielded, because we're more exposed to the external magnetic field, will simply require a lower or a weaker magnetic field to resonate. Sometimes this is referred to as the weaker magnetic field or low field. Down field is another term that's used. Up field over here, stronger magnetic field, and sometimes you see or come across the word higher field there too.